So today I'm going to talk to you about how islands form, and it actually isn't that straightforward of a question because there are many islands, and there are many different ways that islands can form in the first place. My historical geology class is here today, and they are working on a project right now about orogenies, which is mountain building. And in some of their mountain building events, islands have a pivotal role, and we'll kind of talk a little bit about that too, so that this will kind of line up with the project they're working on as well. I put this up because this is a really iconic picture, and actually I have to be honest that as an oceanographer, I always focus so much on the wave part of this that I almost forgot that actually there's an island in the middle of it as well. This is of Mount Fuji, which is one of the major pinnacles of the island of Honshu, which is in Japan. And the population there is a high concentration of people, right? And so islands aren't just important for thinking about them in general or maybe some beautiful tropical vacation. In this case, there are millions of people that live there. And so thinking about how they form and understanding some of the hazards associated with them is important for the populations that live on islands. So I thought of a few different questions that we will come to address as we go through talking about how islands form that we kind of have to think about before we get to the point where we understand how they're forming. So like, what is an island in the first place? And what's the difference between an island and a continent? And I put this picture here because Greenland is considered an island and Australia is considered a continent, but really, in the grand scheme of things, they aren't very much different in size. And so where do we draw that line? And so we'll kind of discuss that kind of thing. What's the difference between an island and a mountain? Are some islands are mountainous and some of them aren't? And so sometimes they're the same thing and sometimes they are not. Then not only how do islands form, but how is new land formed in the first place, even continental land? And then kind of central to our question about what is an island in the first place and how do they form is also how are they destroyed? How do you get rid of an island? So we'll kind of address these as we go along. One of the fundamental things to think about the dynamics of island formation, one of the things that we need to understand is that there is a difference between continental crust and oceanic crust. Continental crust is less dense, and it's either made up of granite or its density is similar to granite. And then oceanic crust is more dense, and it's similar to basalt, or made up of basalt. And so when we think about the dynamics of what's going on the planet, when we think about the density of these two different rocks that make up a lot of the planet, the granite will be less dense and not want to sink down, and the basalt actually becomes denser than the layer below, and it wants to sink. It becomes heavier as it cools. It's a igneous rock. It's a solidified melt. It's a kind of a rock type that makes up the ocean crust. So one of the first ways that we get island formation is related to plate motion. So when two plates come together, that's at a convergent boundary. And depending on what type of ocean crust, or what type of crust, either oceanic crust or continental crust, then we get a different scenario. So if we have an ocean crust topped lithosphere coming towards a continental crust topped lithosphere, we get something called a subduction zone, where the ocean crust, remember, it becomes denser and wants to sink, gets recycled back into the mantle. In this scenario, because there's land on this side, it's not an island that's formed, it's just mountains, right? If we have continental crust, neither one wants to sink. It got there in the first place by this process, right? Where a subducting oceanic crust was dragging it along. the continent doesn't want to sink, so when it collides with another continent, then it builds up and builds like the Himalayas, right? So again, mountain building. But this isn't really an island. Where islands come in is when you get oceanic crust colliding with oceanic crust, and then you get these island arc volcanoes, right, from the melting that occurs when you bring this oceanic lithosphere back into the mantle. So this type of island formation is probably the most common type of island formation on the planet. So places like Japan, places like Indonesia, the Philippines, New Zealand is volcanic, is a subduction zone. Question?
Are trenches synonymous to these situations?
Yeah, so a deep ocean trench would form at this kind of notch where the two plates are meeting. Okay, so the Marianas Trench, right, the deepest part of the ocean, is associated with the subduction zone. Okay, so nearby to that trench are explosive volcanoes.
And you could have remnants in that picture on the right, remnants of continental crust as well as that volcanic volcanism causing an island. I'm thinking of Haida Gwaii, one of the islands I'm going to do, because it's both. It's not only just formed by volcanism like that, but there was some remnants of continental crust in the ocean there, and they are also being kind of smooshed into mountains. So that's kind of a combination.
Yep, exactly. Okay, so there's a lot of many examples of island arc volcanism. Well, one example of that is in the Caribbean. So the Caribbean islands, this is a subduction zone along this part. So the Caribbean plate is over here to the left, and the Atlantic plate is here, and it's subducting underneath, right, the Caribbean plate. And so the Lesser Antilles, this entire chain of islands, is all explosive volcanism related to subduction of the oceanic lithosphere on this side underneath the Caribbean plate on this side. One little extra island formation example that I wanted to show, right, if we zoom in here, okay, you can see here's the arc volcanism. And I didn't really mention these other islands along the way. They're also associated with subducting lithosphere and arc volcanism through time. So a long time ago, some millions of years ago, this subduction zone actually migrated from over here to here to here to here. And so a lot of the island formation on the edge is related to that former arc placement. So this is a boundary in transition, right? That it wasn't always sitting here in the same place, right? That it's migrating. But the other example I wanted to focus on here is at Barbados, because it's kind of an interesting case. So it's located here close to the arc volcanism, but it isn't an explosive volcanic island. If we look at a cross section, so if I drew a slice right there, it would look like this. So here are the Lesser Antilles, the island arc, the explosive volcanoes that are a bit to the west, right, of Barbados. But Barbados actually is from the sediments that are being scraped off the downgoing slab. So as this subducts, all the sediments there are getting kind of plowed off, almost like a snowplow, right, at the front end here. And all that sediment is kind of piling up, and it's piled up high enough that some of that sediment sticks out of the ground, above the water, okay? And that's Barbados. And so I have another cross section that shows this part zoomed in, just because it's kind of interesting. So this part, they call it an accretionary prism. That's just where the sediments had built up at this notch where the oceanic crust is going down, and those sediments are being scraped off and added. They're kind of underplated, right, built onto the underneath. And they're even being kind of intruded into neighboring layers of sediment. So this makes it kind of an interesting puzzle, especially my historical class, as you think of your orogenies and mountain building events. When we go back in time and try to interpret what was going on, something like this, right, finding these sediments later where the younger ones are underneath the older ones, it gives us kind of a like head scratcher of like, wait, how did that happen? Right? So this can be quite complex, these collisions, right? This is a map showing where different subduction zones are. So what you should look for here is this boundary that has the little teeth. So anywhere where there's these dark red triangles. These are all places where there are subduction zones, okay, where explosive volcanoes are being created. Along the west coast of South America, right, that would just be building the Andes Mountains, okay? So in this case, it's not islands, right? But it's the same process. So any place where there's ocean on either side, islands are being created, right? All along subduction zones. Even in the Mediterranean, right? You guys have heard of Pompeii before, right? Big, buried in volcanic ash, right? Explosive volcanism associated with subduction. That's not the end of the plate tectonic story. There's also a way to make islands when you have divergence, where you have spreading, which is kind of weird to think about. In this case, we're just forming new ocean crust, okay, where it's spreading apart. And that's what happens. As you pull two plates apart, the asthenosphere, which is the next layer underneath, just rises up and fills in the gap. It melts because it's rising. It's called decompression melting. And it just passively forms new basalt, new ocean crust. That doesn't really make an island in and of itself, right? That would just make new seafloor. Where we do make new chunks of land that can be surrounded by water, right, which is our sort of rough definition of an island, is where we get rifting, continental rifting. So eventually we can make brand new seafloor by splitting apart a continent. So this is an example of the East African rift. This is a future island. It's not an island yet, right? But right now, there is divergence occurring along this rift system. And you can kind of see this is like one step into the future would be a little skinny ocean, right? And maybe a little bit wider, and then eventually a wider ocean in between. And so eventually this chunk of land right here will break off from the eastern side of Africa, and now then this would be a new island, right? That is made now of continental crust instead of explosive volcanism for its composition. Millions of years. Okay, so here you can see kind of the timeline. This is a different example, but a similar type of thing. And actually just happens to be in a similar area. So this is back when we had, remember Pangaea, if you've heard of Pangaea before, supercontinent, right, where there's continents all connected together. When Pangaea began to break apart, right, so this is 170 million years ago, there was a chunk here, now called Madagascar, that was caught up in the middle of all this. And as it split apart, it was actually attached to the continent of India, right, which had not yet run into Eurasia to build the Himalayas. So this is 135 million years ago that's still attached to India. What happened then was that it rifted, right, and that there was a spreading zone and a new ocean being created between Madagascar and India. The Seychelles Islands also got caught up in this whole spreading. So India actually broke off from Madagascar, and India kind of went screaming up to run into Eurasia. I always imagine that India should be currently making this like crashing car noise, like, right, because it's still colliding at the moment. And Madagascar was a chunk of this continent that sort of got left behind as they rifted apart, right? So this began as kind of little skinny ocean, and eventually the entire Indian Ocean separates Madagascar from India, modern day, right? Yep, yeah, they're actively growing. They can, yeah, that's the whole Tibetan plateau is actively uplifting. Okay, and so timeline, it hadn't rifted quite yet here, right? It started to rift here, and it's more separated there, and then, you know, modern day, we know India is further away. So that's 88 million years. That took, you know, 28 or so to get here. You know, so you can look at kind of spreading rates for that. The rule of thumb is that plate motion is about as fast as your fingernails grow. So That's
The
for a
Atlantic
reference.
Ridge is 2 to 3 centimeters a year.
Okay, and so we can look at places that have divergence to say, here's a future island, right, as it breaks apart. New Zealand is complicated because it has a subduction zone, and I don't know if you can tell, but the triangles point this way over here, and they point this way over here. So there's subduction, the teeth, right, point to the overriding plate. So this is the overriding plate, and there's subduction of the India-Australian plate under over here, and then the Pacific plate is actually subducting under over here. And so there's this really kind of complex scenario going on here. And that you can see kind of the lighter blue here. This is actually a whole land mass that was rifted off of Australia too. So there's all sorts of complex things going on with New Zealand.
Going one way and the other island's going the other way.
Yeah, right, and then it's got kind of this weird pivot point in the middle, right? So tectonically, it's a pretty interesting location.
Are you talking about north versus south
Island.
islands in New Zealand?
Yeah, I don't know where exactly the transition point lands, if it's actually between the two islands, or if it looks like they just sort of have a dotted line there to imply there's something kind of funky, right? And so it might be a transform fault in between, and where that pivot point exactly is, I'm not sure.
Antarctic and Arctic are just kind of stationary, huh?
Well, so the Antarctic plate is surrounded by spreading ridges, so it's sort of everything is falling away from it in a way. But also remember that this is a projection of a globe, right? So it's necessarily distorted, right? That the size of Antarctica here is really stretched out. That actually if this was on a globe, Antarctica would probably be about the same size as this lobe of Africa, right? So if you're looking at it in terms of how much of the planet does what thing, right? Just remember that this is distorted, even though it looks normal to us.
Crashing into those, like the Antarctic continent at all?
No, it's surrounded by spreading, by divergence, the whole way around. So not at the moment. In the past.
Well, that's a safe
Yeah.
place to be there.
Yeah, sure, right? It's a little cold though, yeah. Whoops. I put this up, and maybe it ties into your thing, but I'm not going to focus on it a lot. You can talk more maybe about it. But I put this up to point out to my historical geology class. We were talking about collisions, and when you have a subduction zone and some piece of land connected to it, right, that if you have that subducting plate, it's carrying along whatever land mass is on it. So any of these ways to form an island, if that's attached to a subducted oceanic lithosphere, then that's going to bring it in and add it on to whatever is on the other side, right? If it's not going to sink down, it's going to accrete, right, or add on to the neighboring island. And so if we look at the geology of Alaska or the west coast of Canada and even the west coast of the United States, there are these series, it's colored in here because there's a connection if we look at the rocks themselves, and they call these terrains or accreted terrains, ones that have been added on. And so all of this landmass, right, that's you know, several states wide, okay, have all been added on from subduction. So this was some island arc at some previous point that got, you know, the ocean crust got recycled, and that island arc wasn't going to sink down, right? It just got rafted on to the continent. And so in that question of how do we build new continent, or how do we destroy an island, right, is we might add it on to the continent, right? So islands mushed together make continent.
Could you point out Haida Gwaii is while you're right there?
I don't know where it is.
Transform fault right along the side of it, where the continental shelf is. Go up, up,
Here?
down, right, nope, right there. That
This is,
long
okay.
scimitar shaped thing. It's got the crust separation right at the continental shelf right off to the west side.
Oh, right here, yeah.
Drops down about 4 miles down, I think. And, but that's a transform fault right there, rather than the subduction, which is going on south and north of it.
Mm-hmm.
And that's
But in the past, it would have been subduction before it became a transform.
right, and there's volcanism there too, and then a fifth of land, so it's eventually going to be crushed up into Canada, right?
Yeah, and it looks like the Pacific is moving north and this is moving south. So I guess maybe eventually it'll get mushed in this direction.
I thought it was moving north.
Yeah, the Pacific is going north, right? Because it's subducting the Aleutian Arc. These islands are all subduction zone, right? The Pacific subducting. So on here, we've just recently talked about rifting a continent, right? Spreading it apart. And there's volcanoes associated with that, addition of melt, right? And all the red blobs on this map are associated with rifting, right? So here's that East African rift, right? So that big red blob is a giant pile of basalt, right? That as that continent is splitting apart, right, it's pooling up and pouring out. And eventually, as that chunk of land breaks away, right, that'll be forming new ocean floor. So this is not rare, right? It's quite common, actually, to have a rifted margin, right? Remember, we were just talking about Antarctica, right? That's surrounded by spreading. And so at some point in the past, it had to have split apart, right? It had to rift. So there's melt associated with that. And so some of these islands, right, are associated with that splitting apart of continents. And like we talked about, this is the Seychelles, right? And there's Madagascar that was a chunk of India, right? But there's some melt associated with that rifting, with that spreading apart. And there's a whole nother, I have to check on my time. I don't want to get too involved, right? I could do another hour of talking, right, about this that I won't do. Of the impact of these kind of melts on the environment, right? Especially the Siberian traps here and the Deccan traps, right? Especially the Deccan was associated with the mass extinction of the dinosaurs. So there's a huge impact, right? Especially if these erupt into carbonate sediments of how much CO2 then gets put into the atmosphere associated with that. And it can be quite disastrous for life on the planet. Okay, there's other melt on this map. The blue blobs are oceanic plateaus. They are most often associated with a different type of melt formation. Another example of this same thing is the island of Hawaii. Okay, so those big blue blobs on the last map and Hawaii have their origins in a mantle plume. This would be a hot blob of solid rock rising up through the mantle, which is this layer underneath, through the asthenosphere, and pooling here and bringing up that temperature with it, also having some decompression melting and that melt migrating up to the surface. Here we get an island chain because the plate is moving over top of this mantle plume. And so not only Hawaii itself, but also the other Hawaiian islands, and also seamounts, right? The islands that are now below water, right? Then we've got the Emperor seamount chain and the earlier part of the Hawaiian chain. And all of those islands are formed from this melt from a mantle plume. Glaciers. Doesn't seem like a glacier would form an island, but actually there are two ways that glaciers can form islands. One of them is from glacial deposits. So here's an example. If this is the glacier, it is always moving away from where it's growing. Okay, so it's almost like a conveyor belt, and it can turf sediments, whatever lands on top or whatever has been eroded off from the ground. And at the toe of the glacier, it sort of dumps this pile of sediments. In Michigan, we're intimately familiar with this. We have a ton of sand and gravel in Michigan that is all related to the melting of the glaciers. At the height of the last glaciation, there would have been about 2 miles of ice over where we sit. And we sat at the end of at the toe of the glacier with all the sand and gravel being carried down from Canada and further north to right where we are. This can form islands, and it has. The toe of the glacier also, you can see the dashed yellow line here. There were a couple of different stages. But Long Island, lots of glacial sediments, Martha's Vineyard, Nantucket, this arm of Cape Cod, right? So these islands here are largely moraine deposit. That's the name of this pile of sediments at the toe of a glacier. Another way that a glacier can form an island is by sea level change. And so this shows what sea level was doing. This is in thousands of years ago, so 0,000 years ago is today, so this would be our present day sea level right about here. And so you can kind of see for the last 5,000 to 6,000 years, we've been about similar to this level. But if we go back to 16,000, 17,000 years ago, mean sea level was actually 100 meters lower than it is present day. Okay? And that means that at that time, the coast would have been at a very different location. And so we can see that when we talk about the land bridge between Alaska and Siberia here, the Bering Strait land bridge, that the coastline would have been this red line here.
The whole state of Alaska was the land bridge? The whole thing?
Yeah, right? This is the land bridge, right? That's currently underwater today, right? This is modern day coastline, is the skinny black line, right? But this whole part would have been land then and exposed. And same thing, right? Like the red line here, right? The east coast would have been, once again wider, right? And 1 times wider maybe than kind of New England today, right? And so this would have been the coastline, 17,000 years ago or so, right? Yeah, you're fine.
Blue where Florida is nowadays, that, I guess I'm not understanding.
Oh yeah, so this map also shows the future coastline if we had today's ice sheets melt. Yeah. So the blue, that Florida is covered in water, and the Gulf of Mexico has intruded, way up to Memphis, is now coastal, is if today's ice sheets continue to melt, right? So that's Greenland and Antarctic, right? They're the ones on land.
The direction it's going slowly.
Yeah, and maybe not so slowly anymore, right? The rate of melt is increasing. So Florida maybe used to be twice as wide, so it's already been drowned by half, right? And if things continue as they are, we'll be no more, right? We'll be just go the way of the continental shelf here. So how does that actually make islands? Well, a really great example of this is the British Isles. Okay, so this is the kind of thing that would have occurred here as well. You can see this shallow bit of land, right? The coastline, as when all the water was in the ice, would have been here. Okay, and so this would have just been a continuous piece of Europe, right? With land all where this light blue is. Okay, so then when we had the melting of the last major ice sheets associated with the last ice age, right, that flooded this land here and made these now islands, right, instead of a continuous piece of land.
Is Iceland off that map?
Yeah, Iceland is there, and that's a different thing, but Anne is going to speak next about Iceland formation, but a different reason for that formation. Okay, and then just to kind of wrap up island formation, there are a couple of biologically deposited ways to get islands. Coral reefs. Coral atolls are ones that ring a sinking island, like a basaltic island that then, once it cools, is dense and makes seafloor, right? You might get a ringed reef like that called an atoll. Or the Bahamas, all limestone and coral related to the formation of those islands there. Biologically deposited also means by humans. This is a kind of funny example, okay? So there was a guy that put together a bunch of plastic bottles and then put some sand on top and then soil and then started growing plants and stuff and made his own island. This one is actually sort of floating and not really attached to the land. But we as humans do build out land, and we change the land, and we fill in bays, and so there are other cases. There's in Dubai, there's a whole man-made island. It looks really funny because it's not naturally formed. It has this very like very human shape to it because it has a pattern. Humans like patterns. So man-made, we can have man-made islands as well. Okay, and so hopefully along the way, we've sort of touched on all of these questions and come up with several different ways that we can form islands. Thank you.